Right. So there are two type of, actually there are multiple type of logic, Boolean logic. Uh, so what we have discussed so far are propositional logic. And sometimes we call it zeroth order logic. Okay. So today we are going to look at predicate logic or the first order logic. So zeroth order logic means we work with propositions. That is why we call it propositional logic. Together with Boolean operators like and, or, not, if, and if and only if. That is what we have been doing. Okay. So today we move on to predicate logic or the first order logic. Again, it's part of Boolean logic because the result is either true or false. And result is true or false. So therefore, again, it's Boolean logic. But this time we are going to use quantifiers in our statements. Quantifiers. The two quantifiers are existential quantifier and universal quantifier. Statement like this: some real numbers are positive numbers. Now you can see all of a sudden it's slightly different, right? All natural numbers are negative. And again, you can say whether it's true or false. But your statement has words like some, all. And people heavily use this kind of statement. So therefore, we must be really serious about these words. So universal quantifier, it's like up, downwards A. Existential quantifier, it's something, the symbol we give is like mirror image of capital E. And these are super simple concepts, but it can be fuzzy at times, depending on the way we use it. Sometimes you can be misled, right? You can be misled. Right? What is meant by universal quantifier? So universal quantifier is used to denote all. If something is true for all possible elements, or something is false for all possible elements, to denote all possible elements, we use this, or we call it universal quantifier. So this represents the concept of all possible values. Okay. So this is the formal definition. For all x in our domain, say there's a proposition called Px is true if every x in D, for every x in D, Px is true, right? Say your domain has x1, x2, x3 up to xn. So we can say that for all x, Px is true if Px1 is true and Px2 is true and Px3 is true and so on until Pxn is true. So then we can say for all x Px is true. That means we can say all x Px is true if it is true for each and every value, all possible values. And if it is false for at least one value, your statement is not valid. When you say all x, it is true. If you find that for at least one value it is false, that's the end of the story. Your statement is contradicted. So therefore, if you want to check whether that this kind of a statement is true, easier thing is check whether it's false. Because if you find at least one contradiction, at least for one value, it's not going to be valid, it's false. And if you can't find any contradiction,
So
then
can you explain it again?
so all x means when we have x1 to xn possible values, if that statement is true for each and every value, all the values, we can say that it is true for all x. Simple as that. Okay. But if you find that for at least one value it is false, so your statement is not correct because you say for all x it is true. Okay. For example, let's say we have, so these are our students and these are our students. So assume we have 10 students and assume all 10 students wearing a hat. All 10 students wearing a hat right now. So then someone will come and say all students wearing a hat. So how do you check whether that statement is correct? So you need to check each and every student and see whether that student is wearing a hat. If all 10 students wearing a hat, that statement is correct. But if you find that at least one student is not wearing a hat, one or more, that statement is false. Because the statement say all x where x is a student is wearing a hat. So therefore, if you want to prove it wrong, you need to find at least one count examples. To prove it true, you need to prove that yes, it is true for each and every right possible values. It's very simple logic. It's just the normal terms we use in day-to-day life. So check if there is at least one count example if you want to prove that it is false. But if you want to prove that it is true, either you must prove that there are no count examples or you must prove that it is true for all the possible values. Okay. So therefore, when someone asks you to check a statement with all for universal quantifier, take some extreme or worst case scenarios. Worst case means there's a higher chance that it is false. And check whether for those worst case scenarios, is it true or false? And if it is false, that's it. That statement is false. But if for the worst cases also, if it is true, so there's a higher chance that this statement is true. Okay. Right. So let's take some examples. So if someone says for all real numbers, x squared plus 2 is greater than 0, it's a proposition. But it's a predicate type proposition. Is it true? True or false? You must be able to say true or false. Yeah. One of the value. So if you can find at least one real number which violate this statement is false. But if you can't find any such scenario, look for the worst cases. Then you need to accept that it is true.
True.
True. That means for all real numbers, when you square it and add 2, it is greater than 0. Correct? Because real numbers include negative numbers, positive numbers, and 0. Anyway, for positive numbers, this is always the case, right? Always positive number square and add 2 is positive. For negative numbers, again, when you square it is positive number. When you add 2, it's greater than 2. So then you need to take the middle one, 0. When it is 0, 0 plus 2 is 2, 2 is greater than 0. Therefore, you can't find any contradicting real number. So therefore, you need to accept this statement is true. What about the second one? For all real numbers, x squared must be greater than or equal to 1. For all real numbers, if you can find at least one real number which contradict this, you can say, okay, this statement is false. But if you can't find such a scenario, you need to accept it.
False.
This is false. Can you give me a contradictory real number for this?
When x equals to 0, it is false.
Yes, when x is 0, 0 squared is 0, 0 is not greater than or equal to 1. Not only 0, something like half, right? So 0.5 square is 0.25. 0.25 is not greater than or equal to 1. So there are infinite number of possible values which violate this. So therefore, this is false. What about the third one?
True.
This is true. So if you say true, of course, I can't ask contradiction, right? Because then I need to check whether is it really. Yes, for natural number means 1, 2, 3, 4, 5, 6 positive numbers. The worst case is 1. 1 squared is also equal to 1. So therefore, obviously, this is true. I can't find any contradiction. Next one.
True.
That is also true because the 1, 2, 3, 4, anything satisfy this. Right, next one.
True.
What about the next one? All x, all y, which is a real number, x squared plus y squared must be greater than or equal to 1. So all x, all y means for any all x values and for all y values. That means no xy combination will violate this. No xy combination should violate this. If you can find at least one combination, then the statement is false. True or false? If false, you need to give me an example, scenario where this is violated. So if you take something like x0, y0, which are both real numbers, obviously 0 is not greater than or equal to 1. So that is good enough to say that this is false. Of course, there are some other fractions like 0.1 and 0.1, which when you square and add it, it's not greater than or equal to 1. What about the last one? Now all x, all y coming from natural numbers. X squared plus y squared must be greater than or equal to 1. That is the statement. True or false? If false, you need true or false?
True.
Yes, this is true, right? So the worst case is 1. 1 squared plus 1
True.
squared is also 2, which is greater than 1. So therefore, obviously, for natural numbers, this is going to be true. Right? So it's not difficult. Right? It's not difficult. Right. So now we'll move on to existential quantifier. So existential quantifier stand for sum in general English, sum. So we can use existential quantifier if it is true for at least one element, more than one element, or even when all are all the elements. Of course, when all the elements it's true, you better use this, but using this is also not wrong. Like for example, when everyone is wearing a hat, I can say that some people are wearing hats. But to be very specific, I should have told that everyone is wearing hat. But if I say some people are wearing hats, still my statement is not wrong. When one person is wearing a hat out of 100, still I can go and say some people are wearing hat. So that is very tricky, right? So just one person is wearing hat, I can go and say some people wearing hat. When everyone is wearing hat also, I can go and say some people are wearing hat. But specifically, I should have told all are wearing hats. But this is also not true. Okay. So when someone says use existential quantifier, how do you prove that it is false? How do you prove that it is false? Because proving it true is easy. Just you need one example, you are done. But proving it false is difficult because you need to prove that for all the situations that statement is false. That statement is false. Okay. So this is the formal definition. Exists X in domain D, Px is true if Px1 is true or Px2 is true or px3 is true, or blah, 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 until pxn is true. And it is false only if px1 is false, and px2 is false, and px3 is false, and so on. So you can see that proving it false is more time consuming. Proving that it is true is easier because you just need to come up with one example. But here you need to prove that it is false for each and every example. Then, of course, you can check ranges and so on rather than taking each and every value, taking boundary values. Okay. Right. See whether you can give me the answers. First one, true or false. X is x, which is a real number, x squared equal 4. That means if you have at least one real number which satisfies this statement is true.
True.
Obviously true, right? Actually, you can find two real numbers. One is -2, other one is +2. So that is good enough. Second one, x is x, real number such that 2x is 5.
True.
That is obviously true because there's a real number called 2.5, and that is the only number that satisfies this, but having one number is good enough. So therefore, this is.
True.
What about the third one? X is x, comma, x is y. X coming from first set, y
True.
comes.
True.
So that means you must find at least one xy combination that satisfies this. Can you give me xy combination that satisfies this? Just one is enough.
2 into 3 squared.
Now, what is your x value? What is your y value? That's all I need.
X value is 3 and Y value is 7.
So if x value is 3, 3 to the power 2 is 9, 9 into 2 is 18. Yes, 18 is greater than 7. So that means we have found one value. One value is enough to say that this is true. Okay. This statement is true. Right. So then we can nest existential quantifiers and universal quantifiers when we have multiple variables. So this means for all x and all y, this is true. Or you can say all y and all x, this is true. Same thing. That means for all x values and all y values, and that means all possible combination of x, y values, this must be true. If you find at least one combination, this is false, that this statement is false. So here, if you find at least one x, y combination, this is true, it is true. Then what about this? For all x values, you pair it with at least one y value. That means for this x value, at least one y value. For this x value, at least one y value. It must be true. Then only we can say all x exists y, pxy. This is all y value. There's at least one x value which satisfies. Okay. And this means there's at least one y value here, sorry, x value here, but for that x value, it satisfies for all y values. These are different things. So this means there's at least one y value, but for that y value, it must satisfy this with all x values. Okay, so these are different expressions. So remember, all x exists y is not same as exists y all x. And exist x all y is not same as all y exist x. These are two different stories. Okay. And we can extend this concept to 3, 4 variables as well. Right, check whether this is true. All x, all y, where x is coming from the set x, y is coming from the set y is greater than x. Now, if you can find at least one count example, this is false. So therefore, look for the extreme case. And if it works for extreme case, it should work for all the cases. What is the extreme case? Your attitude is challenge this, right? So you are very offensively, you look at this with the objective of finding a data that contradicts this. That is how you tackle all situations. Right. So the worst case is, remember this statement says y is greater than x. Y is bigger than x. So therefore, let's take the smallest y. Smallest y. And let's take the biggest x. Because that is the worst case. And check whether it still is it going to work. So my smallest x y is 10. Biggest y, x is 7. Yes, 10 is greater than 7. So your biggest guy is also bigger than my smallest guy. So then, of course, it's going to work for all my guys. Because I took my smallest guy and checked with your biggest guy. So if it is also satisfied, definitely it is going to satisfy for all the situations. I don't need to check one by one. So therefore, this statement is true. Okay. What about this? Again, take the now this one is tricky. This one is not all x, all y. This one is x is x, all y. So therefore, you need to be very careful now. That means you must be able to find at least one value from x, but it must satisfy this for all values of y. But you need just one value from x, but for that value, it must satisfy this with all combination of y's. Now I'll go for the best scenario, best case, because I just need to show it for one value. So therefore, I will take the best case is, I will take the biggest x, 55. Right. Now it must be bigger than all the values in y. All the values in y. Yes, 55 is bigger than 10, 5, 20, and 50. Yes, the statement is true. Okay. I found one value in x which is bigger than all the values in y. Do the second one. Now this one is easy because x is x is y. That means if you can find at least one pair that satisfy this, that is the end of the story. At least one pair. Obviously, right? For example, if you take x is 20, y is say 10, right? Obviously 20 is bigger than 10. So there are plenty of combinations, right? Just you need to find one. Even if you take 15 and 5, 8 and 5, you can see 15 and 10, so many possibilities. We just need one. Right. Let's do this example. So just take a little bit of time because it can be tricky sometimes. Remember, x and y are real numbers. X and y are real numbers. For all x, all y, x plus y equals 0. True or false? If it is false, you need to give me a counter example. Counter example means you must give me x and y value which counter this argument.
False.
Can you give me a counter Example.
If we take two negative numbers, it won't be equal to 0.
Yeah, if you take something like
Or
-2 and -3, that is not 0. Therefore, obviously, two negative numbers, two positive numbers. Even though you take positive and negative numbers, if they have different quantities, so this is false, definitely. What about the second one? For all x, x is y such that x plus y is 0. If you can find the contradiction, straight away you can say false. If you can't find the contradiction, you need to accept this.
True.
true.
True. Of course, if it is true, you don't need to give examples, right? Because can anyone come up with a count example? I can't. Because if you take x as from any number from -infinity to +infinity, right? If it is a negative number like -100, so then I can find y value as +100. If my x is 0, y also real number 0. 0 plus 0 is 0. If my x is a positive number like +12, then I have the y as -12. So always for any value of x, there's exactly one y value that make this summation 0. So therefore, yes, we have only one y value, but that is good enough. But it satisfy for all x values. So therefore, second one is true. Third one. Now this is a tricky one. Because this is not all x exists y. This is exists y all x. Left right matters. That means there's at least one y value, but for that y value, this equation must be satisfied for all x values.
False.
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 So that is false because there's no such value. For example, if you take x equal 5, so this is satisfied for y equal -5 only, but not for all. Sorry, let's say your y is +5. So then this is satisfied only for x is -5. But it must, for that y value, it must satisfy for all x values. Therefore, this is false. There's no such possibility. What about the last one? True or false?
True.
That is obvious, right? So that means you must find at least one xy value pair that is of course not one. You can write key, say 0 and 0, 5 and -5. Right? 2 and -2, -3 and +3. So just you need one pair, but you have infinite number of pairs. Can you tell me whether this is correct? Exist y, all x, exist x, all y, x plus y is y. True or false? If it is false, you need to give me a count example. With x and y are real numbers, okay? If you say false, you must give me a count example. Otherwise, if you say true, I will give you a count example, or I will accept. That means if you say true, you don't need to give me example. But if you say false, you need to give me a count example.
True.
False.
False. Then give me example.
If we add -2 and +1, we'll get -1.
And plus 1. Then -2 plus 1 is not plus 1. So
So
therefore,
-1.
okay. But remember, if I can find at least one x value that satisfies this, that is good enough. Any other answer? So I will say no. I can give you an example. So you say no because there's a count example, right? But here it is exists x. I will say I can give you a x value for that x value for all y values. This is satisfied. I can give you example. If I can give you example, it is true. I can give you example. What is that x value? What is that x value that satisfy this formula for all y values? If you can find just one x value, that is good enough. But it must satisfy for all y values. So that value is what? X equals 0. If you select x as 0, it doesn't matter how much you are adding, the result is this value. Say you add 5, result is 5. You add -3, the result is -3. So there exists a value for 0. For that, if you add any value for that, the result is the same value. So therefore, this statement is true. This statement is okay. So this is another way of thinking. So I think today is a really good day for your IQ. I hope your IQ level has now increased. Your capacity has increased. Okay, more than we started the 8 a.m. in the morning. Right. So there are some equivalences which you don't need to memorize, but you need to appreciate. Right. So if someone says all x, px and qx, you can see there are parentheses. So it is equivalent to all x px and all x qx. Okay. So if this is the case, this is the case. Okay. And also, if this is the case, this is the case. If someone says all x px and all x qx, that means all x px and qx. And it's true for existential also. If there's exists px or qx, that means there's exists ex px or ex qx. Okay. But these are not equivalent. This is n. If you all with O, all x px or qx doesn't mean all x px or all x qx. No, there's no such connection. And for existential, it is not going to work for n. Ex px and qx doesn't mean ex px and ex qx. Okay. So this doesn't imply this. This doesn't imply this. Sometimes you get fooled thinking that this implies this implies this. But you must know that no, there's no such thing. If someone tell like this, if you are a logical thinker, you must straight away say, no, there's no such thing. You are lying. You try to fool me. You are a crook. You try to cheat me logically. Okay. So this little bit of a explanation, a little bit of explanation that there's no, this is not correct. So this explanation of this one is not correct. So this is one way, but not the other way. Okay, but not the other way. So if someone says EX, PX and QX, that means EX, PX and EX, QX, but not the other way. Just because you have EX, PX and EX, QX, you can't say EX, PX and QX. Think about it, okay? Right, so then we have, you don't need to memorize these things, okay? But get a feeling of it. So this is called De Morgan's law for first order logic. If someone says not all x px, so that means x is x, not px. Can you give me a real world example? Okay. Say this is our class. These are the students. These are the students. Someone will come and say you have not visited there, right? Someone will come and say if I say all x px, that is false. Okay. Say let's assume that some students are wearing hat. At the same time, some students are not wearing hats. So some students are wearing a hat, and some others they have not wear any hat. So therefore, it's we can say all now you can we say all x px? No, but he can say not all x px. හැමෝම තොප්පි දාගෙන ඉන්නේ නැත. ඒක මොකද? හැමෝම තොප්පි දාගෙන ඉන්නවා කියලා කියන්න බෑ. මම කියන්නේ මට කියන්න බෑ. හරි? හැමෝම තොප්පි දාගෙන ඉන්නවා කියලා යාට කියන්න බෑනේ. දැයි because there's at least one student exists without wearing a hat. So when someone says where everyone wearing a hat is false, that means there's at least one person not wearing a hat. Same. So these two statements are the same. Either you can say there's at least one student not wearing a hat. There exists a student not wearing a hat, which is equivalent to say we cannot say that everyone is wearing a hat. Same meaning. Two statements. Two statements, same meaning. So what about this? Everyone is not wearing a hat. So what kind of situation I can say like this? Everyone is not wearing a hat. So that means the situation is like this. No one is wearing a hat. So then this statement is correct, right? Not PX, everyone. Not means not wearing a hat. Everyone is not wearing a hat. So which is equivalent to not existing anyone with wearing a hat. There is no one exists wearing a hat. Yes, no one exists wearing a hat. Either you can say not EX PX or you can say all X not PX. මේක එකපාරට පොල් මම ඔබ බැලුවම හරි. ඒකට කවුරු හරි මෙහෙම කියෙව්වත් එකයි මෙහෙම කිව්වත් එකයි. ඒලා බලන්න මොකද්ද මේ කිව්වේ? Either he can say like this or he can say like this because these two are equivalent. These two are equivalent. මිනිස්සු ආවිලා කියනවා හරි. ඒකට බුද්ධියක් තියෙනවද මේ මොකද්ද කියන්නේ කියලා. සමහරු හැමෝම Right. So that is De Morgan's law. You need to memorize it, right? Just then and there you can double check using your common sense. Of course, if you can remember it, that is also good. And next one is double negation rule. So when someone says all x px, that means everyone is wearing a hat. All x px. So that means everyone is wearing a hat. All x px means that. And that is equivalent to not px not exist. ඒ කියන්නේ තොප්පි දාපු නැති අය exist වෙන්නේ නැහැ. ඕ ඉතින් නැහැ exist වෙලා නැහැ. Not px does not exist. Yes. So when not px exist is false, that means all x px. So these two are equal. So you don't need to memorize it, but if someone says like this, you must be able to check whether this statement is equivalent or not. So if someone says at least one exists with px, at least one satisfy px. එක්කෙනෙක් හරි තොප්පි දාගත්තා ඉන්නවා. So it is equivalent to say that not everyone is not px. හැමෝම තොප්පි දාගත්තේ නැති අය නෙමෙයි. ඔව්. එක්කෙනෙක් හරි ඉන්නවා කියලා තමයි මෙයා කියන්නේ. That is what exactly this guy is also saying. So these two statements are not contradicting. These two statements are in harmony or equivalent. These two statements are equal. You don't need to memorize, right? But if someone say like that, you must be able to check and your logical thinking and say yes or no. Right. So this is another one. This is a little bit more challenging. For all x, px implies qx. Whenever x happen, q happen. Sorry, whenever p happens, q happen for all x. For all x. So it is equivalent to say that for all x, not px or qx. It's same as p implies q means what? Not p or q. And then we can use it with universal quantifier. පාට පුළුවන් මේක මතක කරලා ඕක අපිට universal quantifier එක දාලා තිබ්බත් වරදින්නේ නැහැ. Okay. And we can use it with existential quantifier also. Exist x px implies qx equivalent to exist x not px or qx. So that means this general rule p implies q is equivalent to not p or q work for universal quantifier as well as existential quantifier as well. කාටට හිතෙන්න පුළුවන් දැන් මේක මා කර්මයන්නේ කියලා නේද? ලොජික්. ඔය ඉතින් කර්මයක් කියන්න බෑ. හැබැයි නැත්තම් අව රවට්ටන්න ඉන්න මිනිස්සු. ඔබ දන්නා ලෝකේ තියෙන අමුතු කතන්දරයක් තමයි මේ ලෝකේ කියන්නේ සාධාරණ දෙයක් නෙමෙයි. Do you think that this world is highly have the justice? No. This world is unfair, right? Imperfect. So in this kind of a world, you need defensive mechanism. And one defensive mechanism is logic. At the same time, you need offensive mechanisms. That is also logic, whether you like it or not. Do you think that you are not offensive? Why not the offensive නෑ කියලා? ඔය හරි අහිංසක මලක් වගේ කෙනෙක් කියලා. I don't think so. වැඩි ඕනෑම මස් මාළු කනවා කියලා හිතන්නේ. ඉතින් එන මලක් වගේ අහිංසක නෑනේ. මස් මාළු කන්නේ. මොකද මාළු ඇවිල්ලා ඔයාගේ ඉස්සරහ දිවිනසා ගන්නවා. ගෙදරට කැරපොත් එක්කම කැරපොත්තත් එක්ක සහජීවනයේ ජීවත් වෙනවා. ඌවේ දොර දානවා. දිගට යනවා නම් ආයි මැරෙන්න හරි ගහනවා සමහරවල්. මීයෙක් ආවම නායක ගැරඩියෙක් ආවම. So world is not fair. But yes, we can try to be as fair as possible and live with harmony as much as possible. But there are plenty of people who try to fool you. And sometimes for survival, we need to do that also. Survival, good things, bad things. To do good things also, you need logical thinking. To do bad things also, you need logical thinking. Whether you like it or not, you can't survive without logical thinking. Otherwise, others will fool you because maybe you are not that vicious, but maybe the people around you are very vicious. Okay? Because you are not living in a perfect world. Right, so this is another one. This is called contrast positive law. For all x, px implies qx is equivalent to for all x, not qx implies not px. Of course, if you can't memorize this, that is fine. Even I don't memorize these things. But can you at least look at it and convince yourself? So if someone says whenever x p, it is q. Whenever p, it is q. For all possible values. Whenever except p happens, q happens. So that means whenever not q, it is not p. Because if p has happened, q has happened. So if q has not happened means p has not happened. But there is no such validity for this kind of statements. All x px implies qx does not equal to all x qx implies ps. මතක නේද අපි normally තේම නේද? p implies q doesn't mean q implies p. And this one, p implies q doesn't means not p implies not q. It work for universal quantifier also. p වුණොත් q වෙනවා කියන්නේ not p වුණොත් not q වුණේ නැහැ කියන එක නෙමෙයි. නේද? ඒ පරණ රූල් එක. Okay. Right, so this is summary of the rules. Summary of the rules. Again, don't try to memorize. If you try to memorize it, it will be a headache for you. But if it naturally remembered, or if you feel like now you are familiar with these things, that is good. Okay. Right. So this is to test your gut feeling. Okay. So unfortunately, the values are not. Let me put it into the. I have not put it into appear. Okay. මතක නැණි කලින් ඒවා දැන්. මතක නැහැ මතක කරන්න. Let's do it. Right. So this is just to give you check your gut feeling, because here we use the word all, some. Use your gut feeling, right? Forget about the theory. Using your gut feeling, because your gut feeling must also get improved when you learn more and more logic and so on. Okay. Socrates is a philosopher. Assume that these are correct. Okay? Assumptions are correct. Valid. All philosophers are poor. Therefore, Socrates is poor. This is a very famous argument. Assuming that the two statements are correct, what do you think about the third statement?
Correct.
So that is correct, because Socrates is a philosopher. All philosophers are poor. Then no, definitely Socrates must be poor. Right. What about the next one? Whenever Anil is here, Kumar is also here. Anil is not here. So therefore Kumar is not here.
Correct.
Correct. So if Anil is here, Kumar is here. Actually, this one is not using all, right? It's normal one. If Anil is here, Kumar is here. But Anil is not here. Anil is not here. Whenever Anil is here, Kumar is here. But Anil is not here. So therefore, you think that Kumar is not here. Are you sure? Are you sure?
Yes.
Sure? It's not a valid argument. So Anil is not. So remember the argument is what? A implies K, but not A. Therefore, K. Now let's assume that these are true. Not A is true. That means not A is true means A is false. A must be false. Now this must be false, but this must be true. When this is false, this must be true, or this can be true. When K is true also, this is true. When K is false also, this is true. Because false implies true is true. False implies false is true. So therefore, Kumar can be present or not present. But this guy says Kumar is not there. Of course, Kumar can be here. Kumar may not be here. So therefore, this can be or may not be. So therefore, this is not an argument. This is not a valid argument. Because remember, when we say whenever Anil is there, Kumar is there, it doesn't mean that it is the only reason for Kumar to exist is Anil exists. Kumar can independently come also. Right? Kumar can independently come. Whenever Anil comes, Kumar can't. Kumar comes, but at the same time, Kumar can independently come. Because this doesn't say if and only if. If they say on if and only if Anil is there, Kumar is there, Anil is there. But this is not like that. Okay. So sometimes your gut feeling doesn't work. Third one. Right. Here we use the word most. So most is not quantifier, right? It's not existential. It's not universal. So therefore, you must be very, 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 very careful. And this is just to give you a hint, but don't look at this. Most drug addicts are depressed people. Most depressed people are lonely. Therefore, most drug addicts are lonely. That is argument. But this one is a tricky argument because we use the word most. So by look of it, you will feel like it is true, right? So that is what your gut feeling says. Usually. That is why you must not always trust your gut feeling. Okay? Because it says most drug addicts are depressed, most depressed are lonely. So therefore, you may feel like most drug addicts are lonely. But this is not a very large. Okay. So look at this Venn diagram. So this is drug addict. This is depressed. Remember, most drug addicts are depressed. You can see that most of the drug addicts belong to depressed circle. Correct, right? Most drug addicts, this is all drug addicts people. Out of these, this is the most bigger part is here and they belong to depressed. Right? So that means correct. That means this diagram satisfies this. Then second says most depressed, that is this circle. And it says most depressed people are lonely. And this is my lonely circle. And you can clearly see that. Okay, let's take something else. So red is depressed. And you can see that most of these red circle guys are in black circle. Black circle is lonely. like lonely people. Black circle means lonely people. So now I have drawn this satisfying both this. Like most of the red guys are in black. Most of the blue guys are in red. Now look at this. Drug addicts are blue. Lonely is black. Do you see that most of the drug addicts are in black? No, most of the drug addicts are not in black. So if this is correct, most of these guys in blue must be in black. But I managed to draw this satisfying these two, but not satisfying this. So therefore, there's a possibility that
Sir,
yes,
but it has a truth value.
what is mean by truth value?
Uh, I mean, yes or no value.
Yes,
So it can't be an argument.
but if I can't be arguing, it's an argument, right? It's an argument, but I showed you is that it's not a valid argument because I came up with you a count example,
Okay.
right? So it's argument, yes, it's argument, but I came up with a count example and proved that there can be situations which contradict your situation because if it is argument, this must be always true. This must be always true. But I came up with a situation example. I use the word most, but at the same time, I came up with an area where it is not right. Most of these blue guys are not in black, but this says most of the blue guys must be in black. So therefore, your argument has issues. There can be situations. This is not correct. This is not correct. So likewise, you can see there are interesting situations. Okay. So shall we give it to the chat GPT? Probably chat GPT may have seen this example because I took it from a particular website. Okay. Let me delete this. So then see how chat AI think about these things, right? It says invalid. The argument does not necessarily follow logically. Necessarily. Can you make a count examples? Mommy kattana වෙන්නේ. Okay. So you can see most does not imply all. And there is no guarantee that the specific individuals who are both drug addicts and depressed are also ones who are lonely. එහෙම මේ හැමෝම වැඩිපුර පිරිසක් එහෙම වෙනවා කියලා මේකක් නැහැ. So now think about how the AI is developed to think like that. Think like that. Right, final one. No, not final ones. Nothing that is cheap is good. Therefore, nothing that is good is cheap. ලාභ දේවල් හිලක් තියෙනවා කියන්නේ nothing that is cheap is good. ලාභ දේවල් කොයි වෙලාවකත් හොඳ දේවල් නෙවෙයි. Nothing that is good is cheap. කියන්නේ හොඳ දෙයක් කොයි වෙලාවකත් ලාභ වෙන්න බෑ.
Valid.
Very. That means cheap things are not always good. So therefore, good things are always not cheap, right? Oh, nothing that is good. That means bad things are cheap, right? Nothing that is good is cheap means bad things are good. Sorry, bad things are cheap, right? So that is a tricky one, right? That means good things cannot be cheap. Good things cannot be cheap. Right, fifth one. So this is an interesting one. John said that everyone loves Mary. Nothing that John has said is true. Therefore, nobody loves Mary.
False.
False. Anyone thinks this is true? John said that everyone loves Mary. Mary. Nothing that John has said is true. John කියනවා හැමතිස්සෙම බොරු. බොරු කියන්නේ එයා කියනවා ඇත්තක් නෙමෙයි. Nobody loves Mary. So this is actually not relevant to each other. This is not relevant to each other. Right? So there's no connection between these two statements. So therefore, this is not a valid argument. Right? So මෙයා මේ බොරුවක් කිව්වයි කියලා අර කතන්දරේ අනිත් පැත්ත හරවන්න බෑ. හරි? එහෙනම් කියනවනේ මෙයා කියන එකේ හැමතිස්සෙම තියෙන්නේ ඒකේ අනිත් පැත්ත කියලා. කියන්නේ මෙයා x y කියලා කිව්වොත් අපි හිතන්න ඕන y නෙමෙයි කියලා. එහෙම එකක් මේ කියලා නෑ. මේ කියන්නේ මෙයා කියන්නේ බොරු. මෙයා බොරු කියනවා කියන එකෙන්
does that mean John is saying meaningless things?
John saying meaningless things. No, whatever John says is a lie. So therefore, what John has told is not a correct statement. Because John says everyone love Mary. Everyone love Mary. So that means no, we know that not everyone love Mary. Because whatever John said is lie. Okay. So therefore, we know that it is false to say that everyone love Mary. But it doesn't mean that no one loves Mary, right? Maybe some people still love Mary. From his statement, what we can take it is not true to say that everyone loves Mary. It doesn't mean that no one loves Mary. Right? That is what I mean by not relevant. Right? But definitely we can say that it is false to say that everyone loves Mary because this guy always tells lies. But it doesn't mean that nobody loves Mary. Those are two different things. Whether not everyone loves Mary is different from nobody loves Mary. Okay. So therefore, this is not a valid argument. Right. So this one is also something like that. Someone is sick. Someone is unhappy. Therefore, someone is unhappy and sick.
True.
True.
Not a valid.
So someone is sick means he is in this category, sick category. Someone. That means there's someone in the sick. There's some sick person. There's at least one sick person. And there are some people who are unhappy. Does it mean that if there's at least one who is unhappy and sick? Because they can be mutually exclusive. Because there's no connection between this. Someone is sick, maybe Nimal. Someone is unhappy, maybe Amal. But it doesn't mean that there's someone who is both unhappy and sick, right? Maybe this guy is just sick, not unhappy. This guy is just unhappy but not sick. Therefore, this is not necessarily true. It can be, it may not be. Right. So now we are done with logic.